when I go into class and sometimes give some good, nice questions for students to try out, sometimes some particular student comes up with a very nice innovative idea of approach for solving that particular question, which is not a routine way of approach which generally teachers teach or which generally you find in books. Sometimes students come up with that kind of an idea. It's the direction of thought process, the raw thinking which is there for the student sometimes sparks so brightly that sometimes you come across a very fine way of approaching certain problems. So this is one such incident where I encountered in class quite recently. This happened. So I'm just going to present the particular topic. It is related to finding omega of moving objects with respect to some observer, and how in one of the problems a student came up with a nice innovative thought process of approach for that particular question, right? So let me present it to you and you can see what kind of a situation that is and what problem that is. So when you need to find omega of an object which is moving in some particular path, so the situation here relates to, you see one object which is labeled as A, and that object is moving along the path of that curve, and there is an observer who is assumed to be at origin, and this observer is observing the object, and velocity of that object is v tangential to the path. That velocity is indicated in the diagram, and the position vector r which is there. So the standard way of finding omega of this particular object as seen by that observer is, whatever velocity is there, you resolve it into two components. So one velocity we call it as v parallel, another component of that velocity we call it as v perpendicular, and these two components are taken along and perpendicular to the position vector. And so it is this v parallel which is like responsible for increasing or decreasing the magnitude of r, and it is v perpendicular which is perpendicular to the position vector, that component is responsible for changing the direction of r. So for instance, if you have a scenario where, let's say, there is an object which is directly moving away from the observer means, so that velocity itself will be only along the position vector. So if there is no v perpendicular, suppose if that is 0, which means that the direction of r will never change, right? So it is in fact that v perpendicular which is creating that angular velocity. So we will be writing from the ideas of circular motion that this v perpendicular will be equal to magnitude of r times omega. So that is what is written over here. V perpendicular is r times omega of object A as seen by that observer O, and it is this v parallel over here, this component, that is responsible for like changing the magnitude of r. So we write it like this: dr by dt will be equal to v parallel. So that v parallel is responsible for magnitude change. Now based on this, here is a question where a student actually came up with an innovative way of approaching the question. Not like this is a routine way, routine way of finding out angular velocity of object with respect to an observer. We follow this routine procedure. So now look at the question. So the question is this: there is an object which is moving along a straight line with a constant velocity of 10 meter per second, and there is an observer who is fixed at point O, such that the distance of the observer from the line of motion is 2 meters. And assuming that the object starts at t equal to 0 directly above that observer, find out whether omega of this object as seen by that observer is going to increase, decrease, or is it going to remain constant with time. So that is the idea behind this question. So the standard way of approaching this particular question, where teachers present the solution, or you can find it in many books. This is standard approach. So what you do, that velocity which is there for the object, you resolve it into two components. One will be along the position vector r, and the other will be perpendicular to the position vector r. So it is the component which is perpendicular to the position vector which is responsible for changing the direction of that r. So what I'm going to be doing here is, I'll be taking r as the position vector, and I can write 10 cos theta. See, what is this cos theta? If I assume that r makes an angle theta with the vertical line, theta will keep on increasing. So here the angle becomes 90 minus theta, and this angle is 90. So the other angle would be theta, and I can write the component 10 cos theta. This is going to be r times omega, but r itself I can write it as from the right angle triangle which you see. I can consider cos theta. If I consider, that is going to be adjacent side divided by hypotenuse, or I can substitute r equal to 2 divided by cos theta, and we can write 10 cos theta equal to 2 divided by cos theta times omega, or omega becomes 5 cos square theta. And in this particular scenario, as the object continuously keeps moving towards right, so theta will keep on increasing. You can very clearly see that theta value will keep on increasing, and hence cos theta will keep on reducing, omega will be continuously reducing as the object moves towards the right. Okay, so this is the regular way of approach. Now let me also tell you the idea which the student got, and how that student's idea was a very a nice way of looking at this particular scenario. So what the idea is, so you wait for every 1 second. So every 1 second this object which is there will keep on covering 10 meters like that. And if you consider the angle swept in every 1 second by the position vector, in the first 1 second, let's say it sweeps an angle delta theta 1, in the next 1 second it sweeps delta theta 2, in the next 1 second delta theta 3, and then the student said that you can see from the diagram that delta theta 1 is more than delta theta 2 is more than delta theta 3. So for every 1 second the angle swept is continuously kind of reducing, so omega should keep on reducing, because by the very definition of the angular velocity, we can consider the average angular velocity will be delta theta divided by delta t. So we are considering regular time intervals of 1 second, and delta theta keeps on reducing. But what is the proof behind this? So when I had asked the student back, how do you prove this, then that is where the student like kind of got stuck. So then I came back home and I worked out on this particular question. Can we proceed on this particular idea and build a mathematical way of exactly proving that this delta theta in fact is going to be reducing with time for regular intervals. So this mathematical build-up which you see below is what I had worked out at home. The student's idea is very, very innovative. So I just thought, okay, this should be kind of approach which could be explained to students in later discussion processes. So when we discuss things in class, as far as science is concerned, we need to be building mathematical relationships to establish for a fact that this delta theta is in fact reducing. There is no room for just making diagrams and saying that in the diagram it appears so, and hence this is what should be the possibility. Well, now we have to rigorously mathematically establish that in fact yes, it is delta theta which is reducing. So for that, what I had done is, so for every 1 second you see that this distance here would be 10 meter, 10 meter, 10 meter, because velocity is 10. And then I'm assuming some angles alpha 1, alpha 2, alpha 3 as the angles, and the corresponding distances of the object at regular 1 second intervals to be L1, L2, L3 from the observer. Now what I'm doing, I'm just taking one particular triangle here and I'm using sine rule in that triangle. So you see the side here which is 10. So 10 divided by sine of opposite angle will be equal to L1 divided by sine of the opposite angle in that particular triangle. So I've written that relation using sine rule. So why am I doing this? So that I can try to figure out what happens to sine of delta theta 2. So from this relation, if you find out sine of delta theta 2, you get sine of delta theta 2 equal to 10 divided by L1 into sine alpha 2, just rearranging it. So you take sine alpha 2 and L1 denominator and bring sine delta theta that side, you will get that relation. So now sine delta theta 2 becomes 10 by L1 into sine alpha 2. Now what I can do for sine alpha 2 is consider this particular right angle triangle, and in that right angle triangle which you see in the diagram, note the angle alpha 2. So sine alpha 2 will be opposite side, which is a fixed distance d divided by hypotenuse. So sine alpha 2 becomes d divided by L2, and hence sine of delta theta 2 becomes 10 into d divided by L1 L2. Likewise, I can now next write sine of delta theta 3 will be 10 into d divided by L2 L3. And as the object continuously moves farther and farther away, we can clearly say that the L1 distance is increasing, L2 distance is increasing. And for the next diagram, see you this relation over here, the product L2 L3 product is more than L1 L2 product, because L1 L2 are kind of smaller values in comparison to L2 L3 product values. So L1 L2 will be lesser than L2 L3. So that being the denominator, we can say that sine of delta theta 3 will be lesser than sine of delta theta 2. Likewise, we can also extend this further and say sine of delta theta 4 will be 10 into d divided by L3 L4, and the denominator will be continuously increasing as the object moves away, and hence this delta theta should continuously fall as the object moves for every 1 second interval. Okay, so this is a very nice way of building up a mathematical model, for which I think I could take the kind of credit, but definitely the idea behind this is a very, very innovative way of thinking and finding out the angular velocity of the object using the very definition. So really hats off to that particular student who actually came up with this particular idea, that yeah, delta theta by delta t kind of reduces with time. Although it appears so in the diagram, we have to still build a mathematical model around that particular aspect of the question.